Orchestrating complexity. Sagas, process managers, and reliable distributed systems. 1. Introduction. The distributed systems conundrum. The modern digital world runs on software. From streaming your favorite show, to ordering groceries online, to managing financial transactions, software powers nearly every facet of our lives. For decades, the dominant approach to building complex applications was the monolith, a single, large codebase encompassing all the application's functionality. This approach served its purpose well for a time, simplifying deployment and internal communication since everything lived in one place. However, as applications grew in scale, complexity, and the demands for continuous delivery increased, the monolithic approach began to show its cracks. Deploying a small change often meant redeploying the entire application, risking disruption to unrelated services. Scaling a single, large application was challenging and often inefficient, as components with different resource needs. Say, a compute-intensive image processing module versus a simple user profile manager shared the same resources. This gave rise to the concept of distributed systems, particularly the microservices architecture. 1.1. The rise of distributed systems and microservices. Imagine a traditional brick-and-mortar store that decides to create an online presence. In a monolithic age, the entire website, from user accounts and product catalogs to shopping carts, payment processing, and order fulfillment, would be built as one massive piece of software. Initially, this might seem straightforward, but as the business expanded, the limitations became apparent. Agility and speed. If the payment team wanted to roll out a new feature, they'd have to coordinate with every other team, test the entire application, and deploy the whole monolith. This slowed down innovation. Scalability. If the product catalog experienced a sudden surge in traffic, the entire application would need to be scaled up, even though the payment or order fulfillment parts weren't experiencing the same load. This was inefficient and costly. Resilience. A bug in one part of the monolith could bring down the entire application. If the product catalog module crashed, customers couldn't load their shopping carts or even log in. Team autonomy. Large code bases often lead to large teams that become interdependent, making independent development and deployment difficult. Microservices architecture offered a compelling alternative. Instead of a single monolithic application, the online store could be broken down into many smaller, independent services, each responsible for a specific business capability. A user service, a product catalog service, a shopping cart service, a payment service, an order service, and a shipping service. Each service is developed and deployed independently, often by a small, dedicated team. The promises of microservices were powerful. Increased agility, independent deployment and scaling, improved fault isolation, and the ability to use different technologies for different services. This paradigm shift was a major catalyst for the widespread adoption of distributed systems. 1.2. The inherent challenges of distribution. While the benefits of distributed systems and microservices are substantial, they introduce a new set of complex challenges that are rarely encountered in monolithic applications. These challenges stem from fundamental truths about distributed computing, network latency, and unpredictability. Services communicate over a network, and networks are inherently unreliable. Messages can be delayed, lost, or duplicated. A request from one service to another isn't instantaneous. It takes time to travel across the wires or wirelessly, and that time can fluctuate wildly. Partial failures. In a monolith, it's generally all or nothing. If one part fails, the whole application might crash. In a distributed system, a single service can fail while others continue to operate. This creates a scenario of partial failure, where only a segment of the overall system is impaired. While this improves overall resilience, it makes the system harder to reason about. How does the rest of the system react when a critical payment service is temporarily unavailable? Data consistency across independent services. This is perhaps the most significant challenge. In a monolith, all components typically share the same database, making it easy to ensure data consistency through traditional database transactions. With microservices, each service often owns its own data store. How do you ensure that a business process, like completing an order, maintains integrity when the inventory lives in one service's database, the payment in another, and the customer details in a third? The fundamental shift from single-process thinking. Developers accustomed to monolithic applications often grapple with a new mindset. Operations that were once instantaneous and assumed to succeed in a single process now involve network calls, potential delays, and the very real possibility of failure at any point. This requires a different approach to designing safeguards and recovery mechanisms. 1.3 Why traditional transaction management falls short. At the heart of reliable software is the concept of a transaction. In traditional databases, transactions adhere to the ACID properties. Atomicity. All operations within a transaction either complete successfully or none of them do. It's an all-or-nothing proposition. Consistency. A transaction brings the database from one valid state to another. Isolation. Concurrent transactions don't interfere with each other. It's as if they are executing sequentially. Durability. Once a transaction is committed, its changes are permanent and survive system failures. For a long time, the software industry relied on this robust model, typically implemented by database management systems. If you wanted to transfer money between two accounts within a single database, an ACID transaction would guarantee that either both accounts were updated correctly or neither was. This was a safe and predictable world. However, the distributed transaction problem quickly emerged with the advent of distributed systems. How do you maintain atomicity, consistency, isolation, and durability when a single business operation spans multiple independent services, each with its own private database? Consider our online store again. When a customer places an order, the order service needs to create an order entry. The inventory service needs to deduct stock. The payment service needs to process payment. The shipping service needs to create a shipment. If any of these steps fail, the entire business transaction must be considered void, and any successful prior steps need to be undone. You don't want to deduct inventory without taking payment or ship an order that hasn't been paid for. Attempts to extend ACID transactions across distributed boundaries were made, most notably through protocols like two-phase commit, 2PC. In 2PC, a coordinator communicates with all participating services. In the first phase, prepare, the coordinator asks each participant if they are ready to commit. If all participants respond affirmatively, the coordinator instructs them to commit in the second phase, commit. If any participant signals it's not ready or fails to respond, the coordinator instructs everyone to roll back. While 2PC technically achieves global consistency, it comes with significant drawbacks in high-scale, high-availability distributed systems. Blocking. Participants must hold resources, like database locks, throughout the entire 2PC process, which can be long-running in a distributed environment, severely impacting throughput and concurrency. Single point of failure. If the coordinator fails during the commit phase, participants can be left in an uncertain state, requiring manual intervention to resolve. Complexity. Implementing and managing 2PC reliably across diverse services and technologies is notoriously difficult. These limitations make traditional ACID transactions and protocols, like 2PC, largely impractical for the kind of highly available, independently scalable, and loosely coupled microservices architectures that define modern distributed systems. Relying on them would negate many of the benefits that microservices promise. 1.4 Introducing the need for sagas and process managers. So, if traditional ACID transactions are too cumbersome for cross-service operations, how do we ensure our distributed business processes are reliable? How do we handle complex workflows where one part failing means other successful parts need to be reversed? How do we orchestrate a series of operations across independent services to achieve a meaningful business outcome without a global transaction manager holding everything hostage? This is precisely where the patterns of sagas and process managers come into play. They represent a fundamental shift in managing consistency in distributed systems, moving away from immediate, global ACID consistency towards eventual consistency. Instead of trying to maintain a lockstep, all-or-nothing approach across multiple services, they embrace the reality of distributed systems. They accept that a multi-step business process might be in an intermediate, temporarily inconsistent state as it progresses, but they rigorously ensure that it will eventually reach a consistent final state, regardless of failures. A saga is a pattern designed to manage distributed transactions. It defines a sequence of local, atomic transactions performed by individual services. If any local transaction in the sequence fails, the saga executes a series of compensation transactions to undo the effects of previous successful local transactions, bringing the system back to a coherent, if not strictly original, state. A process manager, often closely related to or the same as a saga orchestrator, is a component specifically responsible for coordinating the steps of a complex business process or saga. It maintains the state of the overall workflow, sends commands to individual services, and reacts to events from those services, deciding the next step, or initiating compensation if a failure occurs. Over the course of this book, we will delve deep into these powerful patterns. We will explore the foundational concepts that enable them, like asynchronous communication and event-driven architectures, the specifics of how sagas work, including their various forms and the critical role of compensation, the architecture and implementation of process managers, leveraging concepts like state machines, practical challenges such as error handling, idempotency, and monitoring, real-world case studies demonstrating their application. By the end, you will have a comprehensive understanding of why sagas and process managers are indispensable tools for building robust, scalable, and resilient distributed systems in today's complex software landscape. You'll learn not just what they are, but how to effectively use them to orchestrate complexity and deliver reliable applications that meet the demands of modern business. 2 foundational concepts: understanding asynchronous and event-driven architectures. Before we dive deeper into sagas and process managers, it's crucial to establish a solid understanding of the underlying principles that make these patterns possible and effective. These principles are rooted in how components in a distributed system communicate and how they manage consistency. 2 concepts stand out as primary enablers: asynchronous communication and event-driven architectures, EDA. 2.1 Synchronous versus asynchronous communication. Think about ordering food at a restaurant. There are a few ways this interaction can happen. Synchronous communication, the traditional way. You sit down, the waiter comes, you tell them your order. The waiter then stands by your table, waiting for the chef to cook your meal and deliver it personally. Only then does the waiter leave your table, and you can pay. This is synchronous. You, the customer, are blocked until the entire process is complete. Asynchronous communication, the more efficient way, you give your order to the waiter. The waiter takes your order to the kitchen and then goes off to take other customers' orders or serve drinks. You wait at your table. When your food is ready, the waiter or another server brings it to you. You are not blocked after placing your order. You can chat, look at your phone, or drink water. The waiter is also not blocked. They can serve others. In software, synchronous communication means that when one component, e.g., Service A, calls another component, e.g., Service B, Service A stops its current work and waits for Service B to complete its task and return a response. This is common in traditional programming models, often implemented via direct function calls or HTTP request-response patterns. Service A, request Service B. Response: Service A blocked, Service A resumes. Benefits of asynchrony in distributed systems. Responsiveness: if Service A doesn't have to wait for Service B, it can immediately move on to other tasks or free up resources. This can dramatically improve the user experience and overall system throughput, especially if Service B's operation is long-running. Decoupling: services become less dependent on each other's immediate availability. If Service B is temporarily down or slow, Service A can continue operating, perhaps by queuing messages for later processing, rather than grinding to a halt. This leads to more resilient systems. Scalability: when services communicate asynchronously, they can process requests independently. If Service B becomes overwhelmed, messages can queue up, allowing Service A to continue sending requests without being blocked. This enables independent scaling of services based on their specific load. Resource utilization. In a synchronous model, resources are often tied up waiting for responses. Asynchronous communication allows for more efficient use of threads, connections, and other system resources. Asynchronous communication is not just about performance. It's about building systems that are inherently more resilient and capable of handling the unpredictable nature of networks and independent services. 2.4 Introduction to Event-Driven Architectures, EDA. Asynchronous communication often finds its most powerful expression in event-driven architectures, EDA. In an EDA, components don't communicate directly via synchronous calls very often. Instead, they interact by producing and consuming events. What are events? An event is simply a record of something that happened in the past. It's a statement of fact. For instance, customer X signed up. Item Y stock reduced by 5 units. Payment Z processed successfully. Order Q shipped. Events are immutable. They represent a point in time. They are typically broadcast messages, meaning any interested party can listen to them. The anatomy of an EDA, event producers. These are services or components that perform an action and then publish an event describing what happened. They don't care who listens or what happens next. Their responsibility is simply to announce the fact. Event consumers. These are services or components that subscribe to specific types of events. When they receive an event they're interested in, they react by performing their own internal logic. Message brokers or event buses queues. These are the central nervous system of an EDA. They act as intermediaries, receiving events from producers and reliably delivering them to interested consumers. Popular examples include Apache Kafka, RabbitMQ, Amazon SQS SNS, Azure Service Bus, and Google Cloud Pub Sub. They provide durability, publish-subscribe mechanisms, and often ordering guarantees. The power of loose coupling and high cohesion through events. EDA significantly enhances loose coupling and high cohesion in distributed systems. Loose coupling. Services don't know about each other's existence or internal implementation details. A service just publishes an event and interested consumers react to it. This means you can add new consumers, e.g., a reporting service that logs all payment events without changing the original producer, the payment service. This drastically reduces inter-service dependencies. High cohesion. Each service can focus intently on its specific business capability. The payment service handles payments, and the inventory service manages inventory. They don't need to know the entire business process flow. They just react to relevant events from their perspective. Eventual consistency as a natural consequence and design choice. With an EDA, consistency shifts from being immediate and global to being eventual. When an event is published, it might take a short amount of time for all interested consumers to react and update their respective states. During this transient period, different parts of the system might be in slightly different states. Consider our payment example. When a payment service processes a payment, it publishes a payment processed event. The order service hears this and updates its order status. The shipping service hears this and schedules shipment. For a brief moment after the payment is processed, but before the shipping service updates its status, the overall system is eventually consistent. The payment is processed, and it will be shipped, but the shipping status isn't updated yet. We'll delve deeper into this concept next. 2.3 Understanding consistency models. When we talk about consistency in distributed systems, it's not a single concept. There's a spectrum, and choosing where to be on that spectrum is a fundamental design decision. ACID Revisited. As discussed in Chapter 1, ACID atomicity, consistency, isolation, durability is the gold standard for transactions within a single relational database. It provides a strong guarantee. Either all changes within a transaction are applied, or none are, leaving the database in a correct and consistent state. This model works exceptionally well when all the data and logic involved in a transaction reside within a single logical unit. However, in a microservices environment, where each service owns its data and operates independently, attempting to enforce ACID across multiple services becomes extremely difficult and often counterproductive due to the issues with distributed transactions, like 2PC we discussed. Introducing base. Because global ACID transactions struggle in the distributed realm, a different set of properties, referred to as base, has emerged as a more realistic and often preferable model for distributed systems. Basically available, the system should generally function and respond to requests, even if some data inconsistencies exist. In a partitioned network, services should remain available and continue processing operations locally. Soft state. The state of the system can change over time, even without input, due to eventual consistency. Data doesn't have to be immediately consistent across all services. Eventually consistent. If no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. This means that after a change, it might take some time for the change to propagate and be reflected across all copies of the data, but it will happen. Why base? In essence, base trades immediate consistency for availability and partition tolerance. The ability of a system to continue operating even if network failures partition the system into multiple isolated subsections. This trade-off is often essential for building highly available and scalable distributed systems. Reconciling immediate business needs with eventual consistency. The idea of eventual consistency can sometimes make business stakeholders uncomfortable. You mean my customer's payment isn't immediately reflected everywhere? In practice, many real-world processes are inherently eventually consistent. Bank transfers. When you transfer money between banks, it's not truly instantaneous. Money might leave your account immediately, but it takes time for it to appear in the recipient's account. This is an eventually consistent process. Package deliveries. When you place an order, the item doesn't teleport. It moves through various stages, packed, shipped, in transit, and the perceived final, consistent state delivery happens eventually. For many business operations, a small delay in data propagation is perfectly acceptable, especially when weighed against the benefits of availability and scalability. The key is to manage user expectations and design the system such that these temporary inconsistencies don't lead to incorrect business decisions. For example, if a user's balance takes a few seconds to update after a transfer, that's usually fine. If they can immediately withdraw money that hasn't cleared, that's a problem. Sagas and process managers are precisely about managing this eventual consistency effectively to prevent such problems. 2.4 Communication, patterns in distributed systems. Building on asynchronous communication and EDA, let's briefly touch upon the common communication patterns. Request-response. This is the synchronous pattern we started with, often implemented via HTTP and REST-TFL APIs. Service A sends a request to Service B and waits for a response. It's generally suitable for queries, e.g., get detailed customer information, where immediate data is needed, or for simple commands that can be executed atomically within a single service boundary. Event-driven, publish-subscribe. As discussed, services publish events to a message broker, and other interested services subscribe to them. This provides maximum decoupling and resilience, especially for scenarios where multiple services need to react to a single change without the producer needing to know about them. This is the cornerstone of sagas and process managers. Commands, while events are facts about the past, something did happen, commands are requests to do something, please do this. In an orchestrated saga, the orchestrator sends commands to participating services, e.g., process payment. Commands are typically sent to a single recipient and imply an expectation of action. They also need to be handled idempotently, meaning that processing the same command multiple times should have the same effect as processing it once. Queries. Like commands, queries are a form of request, but they are specifically for retrieving data and should not cause any side effects on the system's state. When a user wants to view their order history, the UI would typically send a query to an order read model or history service. Understanding these foundational concepts, the benefits of asynchrony, the power of event-driven architectures, and the nuances of consistency models is crucial for grasping why and how sagas and process managers operate. They are not merely design patterns. They are architectural responses to the inherent complexities of distributed systems, designed to enable resilient, scalable, and manageable applications in a world beyond the tightly coupled realm of single-instance ACID transactions. With these building blocks in place, we can now precisely articulate the problem that sagas and process managers are designed to solve. 3. The problem of distributed transactions. Why ACID alone isn't enough. In Chapter 1, we touched upon the limitations of traditional ACID transactions when trying to span multiple independent services. In Chapter 2, we explored the foundations of asynchronous communication and event-driven architectures, highlighting how these approaches move us towards eventual consistency. Now, it's time to fully unpack the distributed transaction problem and articulate why the strategies we'll soon learn about, sagas and process managers, are not just optional niceties, but essential tools for building reliable distributed systems. 3.1. The illusion of global transactions. Let's reiterate a critical point. In a microservices architecture, where each service typically owns its own database and is deployed independently, the concept of a single, all-encompassing ACID transaction spanning multiple services is an anti-pattern. It directly contradicts the core tenets of microservices: autonomy, loose coupling, and independent deployability. Trying to force a global ACID transaction often leads developers down the path of technologies like the two-phase commit, 2PC, protocol, or sometimes variations like XA transactions. While these protocols technically achieve atomic commit across multiple resource managers, like databases, their practical difficulties in a highly available, high-scale distributed environment are well documented. Blocking resources. During the prepare phase of 2PC, all participating services are required to lock their resources until the commit or rollback decision is made by the coordinator. In a system where network latency or service unavailability is a given, these locks can be held for extended periods, leading to severe performance bottlenecks, reduced concurrency, and even deadlocks. Imagine a large e-commerce site where product inventory and payment systems are locked for seconds or minutes every time an order is placed. It would be catastrophic for throughput. Single point of failure for the coordinator. The 2PC coordinator is a critical component. If it fails after participants have prepared, but before the final commit rollback decision is broadcast, the participants are left in an in-doubt state. They are still holding locks, waiting for a resolution that may never come or may require manual intervention. This significantly reduces overall system availability. Performance overhead. The multiple rounds of communication between the coordinator and participants add significant latency, making 2PC unsuitable for high-performance applications. Complexity. Implementing and maintaining 2PC configurations across heterogeneous technologies is notoriously complex and brittle. In short, while tempting for their promise of strong consistency, distributed ACID transactions, like 2PC, are generally considered detrimental to the goals of building robust, scalable, and highly available microservice systems. They couple services too tightly, introduce bottlenecks, and are prone to difficult-to-resolve failures. 3.2 Business processes spanning multiple services. Now that we've established why global ACID transactions are out, let's explore the fundamental problem that remains. Many, if not most, meaningful business operations naturally span multiple independent services. These are the distributed transactions that we must manage reliably, even without a global ACID guarantee. Let's consider a common scenario: an online retail order fulfillment process. When a customer clicks Place Order, several things need to happen across different services. Order service needs to record the new order in its database, assigning it a unique order ID and an initial pending status. Inventory service needs to deduct the ordered items from stock. Payment service needs to charge the customer's credit card. Notification service needs to send an order confirmation email to the customer. Shipping service needs to create a shipment request. This seemingly straightforward process immediately highlights the distributed challenges. What happens if payment fails after inventory is deducted? The customer hasn't paid, but your inventory reports are now incorrect. You've essentially given away products. What happens if shipping fails after payment is confirmed and inventory is deducted? The customer has paid and the stock is gone, but the product isn't being sent. You have an unhappy customer and a potentially unfulfilled promise. What happens if the notification service is down when the order is placed? The customer might not receive confirmation, leading to confusion, even if everything else succeeded. This is the core of the distributed transaction problem. How do we ensure that either all these steps logically succeed as a cohesive business process, or if any step fails, we can effectively undo the prior successful steps, leaving the system in a consistent, meaningful state? Without a coordinated approach, these partial failures can lead to data inconsistencies, loss of business revenue, unfulfilled customer expectations, and a nightmare for operational teams. 3.3. The need for long-running business processes. Many critical business workflows are not instantaneous. They involve multiple steps that might be separated by significant time intervals, potentially involving human intervention, external system calls, or even waiting for real-world events. These are often referred to as long-running business processes. Examples include loan application approval, involves credit checks, background verification, manual review, and approvals spanning days or even weeks. Travel booking. As per our initial analogy, booking flights, hotels, and rentals can involve external third-party systems and human choices. Manufacturing workflow. Procurement of raw materials, assembly, quality control, packaging, and delivery. For such long-running operations, traditional ACID transactions are entirely unfeasible. You cannot hold database locks for days while a human reviews a loan application. The atomic nature of ACID transactions implies near-instantaneous execution. This is where the concept of compensation becomes paramount. If a long-running process fails at some intermediate step, e.g., a credit check fails in a loan application, we can't simply roll back the entire system state as if nothing happened. Changes might have been made to external systems or physical resources. Instead, we need a way to reverse or undo the effects of the completed steps. We need to compensate for them. If a pre-approval was issued, it needs to be revoked. If a preliminary credit score was pulled, it might need to be noted that the application failed. Compensation acknowledges that some actions are irreversible or only partially reversible in the real world. It aims to put the system into a business-consistent state, even if not an identical prior state. 3.4. Introducing the core problem solved by sagas and process managers. The fundamental problem sagas and process managers solve is managing consistency for long-running, multi-step operations in a distributed environment without relying on global ACID transactions. Instead of a single, indivisible transaction, they offer a framework for breaking down complexity, decomposing a complex business process into a series of smaller, independent, atomic local transactions. Coordinating steps, ensuring that these local transactions are executed in the correct sequence, often driven by events. Handling partial failures gracefully, providing explicit mechanisms to react to failures at any stage, primarily through compensation transactions. If one step fails, the system doesn't crash. Instead, it executes specific, undo actions on the previously completed steps to restore a consistent business state. Embracing eventual consistency appropriately, acknowledging that for a brief period, the overall system might be technically inconsistent during the execution of a multi-step process, but guaranteeing that it will reach a desired consistent state eventually, whether through successful completion or successful compensation. Sagas specifically address the atomicity of a distributed transaction by guaranteeing that either all local transactions within the saga complete or a series of compensation transactions are executed to undo the effects of any completed forward transactions. They ensure that business integrity is maintained despite the distributed nature of the operations. Process managers provide the overarching control and state management for these complex, multi-service workflows. They are the brains that orchestrate the commands and react to the events, ensuring the saga progresses correctly or is compensated effectively. By understanding the severe limitations of global ACID transactions and the inherent challenges of managing consistency across independent services, we can truly appreciate the elegance and necessity of the Saga and Process Manager patterns. They offer a robust and resilient path forward for building the highly concurrent, scalable, and reliable distributed systems that power our digital world. The next chapters will show you exactly how to implement them. 4. Introducing Sagas, a pattern for distributed consistency. Having established the limitations of traditional distributed transactions and the complexities of managing long-running business processes across independent services, we are now ready to introduce Sagas. The Saga pattern provides a powerful and practical solution for achieving eventual consistency in these challenging scenarios. 4.1. What is a saga? An intuitive definition. Imagine you're trying to build a complex structure, like a house. What if you couldn't build it piece by piece? What if you had to have every single brick, every piece of wood, every window, and every appliance delivered all at once, and then, in a blink, the entire house just appeared? That's what a traditional ACID transaction implies. Everything happens atomically or nothing does. But building a house, in reality, is a multi-step process. Lay the foundation, build the walls, put on the roof, install the plumbing, connect electricity, and so on. Each step is a distinct action. What if, after laying the foundation and framing the walls, you discover that the land isn't stable enough for the planned structure? You can't magically unlay the foundation. Instead, you need a plan to return the site to a stable condition, perhaps by removing the frames and reinforcing the foundation. These undo actions are crucial. This is an intuitive way to understand a saga. A saga is not a single, giant, atomic transaction. Instead, it's a carefully coordinated sequence of local transactions, where each local transaction updates data within a single service, its own database, and then publishes an event. This event triggers the next step in the saga. The critical innovation of the saga pattern is its built-in mechanism for dealing with failure. If any step in the sequence fails, the saga initiates compensation transactions. These compensation transactions are designed to undo the effects of the previously completed local transactions, ensuring that the entire distributed business process either completes successfully or is gracefully rolled back to a consistent state. It's a mechanism for achieving eventual consistency by guaranteeing that once a distributed business process starts, it either finishes or its impact is reversed. Key characteristics of a saga: no global ACID transaction. It explicitly moves away from trying to perform a single, all-encompassing atomic transaction across multiple services. It acknowledges the autonomy of individual services, relies on eventual consistency. During the execution of a saga, the overall system might be in a temporary, inconsistent state from a global perspective. For example, inventory might be reserved before payment is fully captured. However, the saga guarantees that the system will eventually reach a consistent state, either by successfully completing all steps or by compensating for failures. Emphasizes compensation. This is the core concept that enables sagas to provide reliability. For every forward step, there must be a defined backward or undo step. This foresight into potential failure is vital. 4.2 Sagas in action. A simple example. Let's revisit our transfer money scenario, but now specifically modeled as a saga between account service A and account service B, each managing its own account balances in its own database. Consider the business requirement. Transfer $100 from account X, managed by account service A, to account Y, managed by account service B. Saga transfer money steps. Step 1. Debit account X. Account service A receives a request. It deducts $100 from account X's balance within its private database. This is local transaction 1, LT1. Upon successful completion of LT1, account service A publishes an event. Account X debited, transfer ID, TR123, account X, $100. Step 2, credit account Y. Account service B listens for account X debited events. When it receives the event for transferred, TR123, account service B attempts to add $100 to account Y's balance within its private database. This is local transaction 2, LT2. If successful, account service B publishes account Y credited, transfer ID, TR123. If LT2 fails, e.g., account Y is frozen or some validation error occurs within account service B publishes. Account Y credit failed, transfer ID, TR123 reason, account frozen, handling failure compensation, scenario, account Y credit failed occurs. A Saga coordinator, or account service A itself, listening for this event, detects the account Y credit failed event for transfer ID, TR123. It then initiates a compensation transaction for LT1. It sends a command to account service A to credit $100 back to account X. This effectively undoes the previous debit. Once this compensation action completes, the system reaches a consistent state where account X has its money back and account Y was never credited. The distributed transfer failed gracefully. Notice the brief, inconsistent state. For the short period between account X debited and either account Y credited or the compensation of account X, in case of failure, the total money in the system, across both accounts, temporarily appeared to be $100 less. This is the nature of eventual consistency. The system guarantees to reach a consistent state eventually through successful completion or compensation. 4.3. The evolution of distributed transaction management. The Saga pattern isn't a new invention. It was first described in a research paper by Hector Garcia Molina and Kenneth Salem in 1987. Back then, it was primarily discussed in the context of long-running database transactions. Its resurgence and popularity today are directly linked to the widespread adoption of microservices and the inherent challenges they pose to strict ACID consistency across service boundaries. As we discussed in Chapter 1, the limitations of 2PC and XA transactions made them unsuitable for modern distributed systems. Sagas provide a robust, resilient alternative that embraces the asynchronous and independent nature of microservices. When to choose a Saga? Long-running business processes. Any operation that involves multiple steps that cannot be completed within a single, atomic, instantaneous transaction. Business processes spanning multiple services databases, when a single logical operation requires updates to data owned by different microservices. High availability and scalability requirements. Traditional distributed transactions often introduce bottlenecks and single points of failure. Sagas avoid these by promoting loose coupling and relying on eventual consistency. Need for explicit error handling and rollback. Sagas force you to think about what if and explicitly design compensation mechanisms. When not to choose a Saga, simple, single-service operations. If an operation is entirely confined to one service and its database, a local ACID transaction is sufficient and simpler. Extremely strict immediate consistency requirements. While rare in true distributed systems, if a business rule absolutely requires global, instantaneous consistency at all times, with no tolerance even for transient inconsistency, then other, often more complex and less scalable, solutions might be considered. However, it's crucial to challenge such requirements, as they often stem from monolithic thinking applied to a distributed world. 4.4 Key concepts for understanding Sagas. To effectively design and implement Sagas, a clear understanding of these core concepts is essential. Local transactions. This is the atomic unit within a Saga. Each step in a Saga is a traditional, ACID-compliant database transaction executed within the boundaries of a single service. For example, when an inventory service deducts stock, this action, updating its database, is a local transaction. If anything within that service's operation fails, that local transaction should be rolled back by the database, ensuring the service's own data integrity. Sagas then coordinate these local transactions. Compensation transactions. These are the undo functions. For every successful local transaction within a Saga, there must be a corresponding compensation transaction that reverses its effects. If you debited an account, the compensation is to credit it back. If you reserved inventory, the compensation is to release the reservation. Compensation transactions are themselves local transactions executed within a single service. Their design is critical, as they must accurately undo the business effect of the forward transaction. It's important to differentiate between compensation and a simple database rollback. A database rollback means the original transaction truly never happened. Compensation means the original transaction did happen, but its effects are being actively reversed by a new, corrective transaction. Events. Events are the communication mechanism that drives a saga. After a service successfully completes a local transaction, or fails to, it publishes an event describing what happened, e.g., order created, payment processed, inventory deducted, payment failed. Other services or a central saga coordinator listen for these events, reacting to them by performing their own local transactions, initiating the next step in the saga, or triggering compensation logic. Events provide the loose coupling essential for distributed systems. Idempotency. This is a crucial property for any operation participating in a distributed system, especially within a saga. An idempotent operation is one that can be executed multiple times without changing the result beyond the initial application. For instance, if you send a credit account message twice, the account should only be credited once. If you deduct inventory multiple times for the same order, only the first deduction should apply. Why is this important? Because messages in distributed systems can be duplicated, e.g., due to retries, network issues, or message broker specifics. If a service receives the same event or command multiple times, it must process it only once or ensure that repeated processing doesn't cause incorrect side effects. Strategies for achieving idempotency often involve tracking unique operation IDs or ensuring database updates are conditional on the current state. By understanding these core concepts, we lay the groundwork for exploring the two primary patterns for implementing sagas, which we will delve into in the next chapter. 5. Saga implementation patterns. Choreography vs. orchestration. Once the decision is made to implement a saga, the next crucial step is to choose how the saga's steps will be coordinated. There are two primary patterns for implementing sagas: choreography and orchestration. Both achieve the goal of managing distributed consistency, but they do so with different organizational principles, each with its own set of advantages and disadvantages. To better understand them, imagine a dance. 5.1 Choreography-based sagas, the decentralized approach. In a choreography-based saga, there is no central director. Instead, each participating service acts autonomously, performing its part and then broadcasting an event. Other interested services listen for these events and react accordingly, performing their own local transactions and publishing new events. The logic of the saga is implicitly distributed among the services, much like dancers in a freestyle routine, each knowing their cues and reacting to the music and each other's movements. How it works. Let's illustrate with a simplified order processing saga using choreography. Suppose an order requires stock deduction and payment processing. Order service receives a request to create a new order. It saves the order in its database, local transaction 1, and publishes an event. Order created, ordered, O123 items, product A, product B, customer ID, C456. Inventory service subscribes to order created events. When it receives O123, it attempts to deduct stock for product A and product B, local transaction 2. If successful, it publishes inventory deducted, ordered, O123. If unsuccessful, e.g. out of stock, it publishes inventory deduction failed, ordered, O123 reason, out of stock. Payment service subscribes to inventory deducted events. When it receives O123, it attempts to process the customer's payment, local transaction 3. If successful, it publishes payment processed, order ID, O123. If unsuccessful, it publishes payment failed, ordered, O123 reason, insufficient funds. Order service compensation logic. In a choreographed saga, the order service would also subscribe to failure events. If it receives inventory deduction failed, or payment failed, for O123, it marks the order as failed in its system. Inventory service, compensation logic. If it receives a payment failed event, it would then perform a compensation transaction, e.g., restoring the previously deducted inventory for O123. Advantages: high decoupling. Services have minimal direct knowledge of each other. They interact only through asynchronous events, leading to a truly independent and highly decoupled system. This can make services easier to develop, test, and deploy independently. Simple for small sagas. For sagas with few steps and simple, linear flows, choreography can be straightforward to implement, as each service only needs to react to a few defined events. Easy to add new steps. Extending the saga, e.g., adding a notification service that sends an email after payment, can be as simple as adding a new service that subscribes to an existing event, e.g., payment processed, without modifying any existing services. Disadvantages: lack of visibility, the biggest drawback. It's incredibly difficult to get an overview of the saga's overall progress or state. You can't ask a single component, "Where is order O123 in its saga flow?" You have to piece together information from scattered event logs across multiple services. Debugging challenges. Tracing the flow of a failing or stuck saga can be a nightmare. It requires inspecting message queues and logs across many different services to understand why a specific step didn't trigger, or why compensation didn't occur as expected. Circular dependencies, deadlock potential. Without careful design, services can inadvertently create complex event chains that might lead to unintended loops or race conditions if event ordering is not perfectly managed. Scalability concerns for complex sagas. As the number of steps, conditional logic, or participating services grows, managing compensation chains, which event triggers which compensation, if multiple events can cause failure, becomes extremely complex and error-prone. The spaghetti architecture anti-pattern, where events fly in all directions without clear overarching control, is a real risk. 5.2 Orchestration-based sagas. The centralized approach. In an orchestration-based saga, a dedicated orchestrator, or saga coordinator, service is explicitly responsible for managing and directing the entire flow of the saga. This orchestrator maintains the state of the saga, sends commands to participating services, and processes events from those services to determine the next step or to initiate compensation. Think of it as a conductor leading an orchestra, telling each musician exactly what to play and when. How it works. Let's use the same order processing example, but with an orchestrator. Order orchestrator, or a dedicated saga manager service, receives the initial order request. It saves the saga's state, e.g., order initiation, in its own database. It sends a command to the inventory service. Deduct command, ordered, O123, items, product A, product B. Inventory service receives deduct command. It performs local transaction 1 deduct stock. Upon completion, it replies an event back to the orchestrator. Stock deducted event, ordered, O123, or stock deduction failed event, ordered, O123 reason, out of stock. Order orchestrator. If stock deducted event is received, it updates its internal saga state to inventory confirmed. Then, it sends a command to the payment service. Process payment command, order ID, O123 amount, XXX. If stock deduction failed event is received, it updates its saga state to failed inventory. It then potentially initiates compensation, e.g., sends cancel order command to the order service if the order record needs to be removed. Payment service receives process payment command. It performs local transaction 2, processes payment. Upon completion, it replies an event back to the orchestrator. Payment processed event, ordered, O123, or payment failed event, ordered, O123 reason, insufficient funds. Order orchestrator. If payment processed event is received, updates saga state to payment confirmed. Sends command to shipping service. Create shipment command, ordered, O123. If payment failed event is received, updates saga state to failed payment. Crucially, it then sends a compensation command to the inventory service. Add stock back command, ordered, O123, items, product A, product B. Advantages: clear visibility. The orchestrator maintains the complete state and flow of the saga. You can query the orchestrator to know exactly what step a particular order, saga instance, is currently in, making monitoring and debugging much easier. Easier debugging. all the saga logic resides in one place. If something goes wrong, you primarily examine the orchestrator's code and its state rather than trying to trace distributed events. Simpler compensation. The orchestrator explicitly manages the entire compensation sequence. If a step fails, the orchestrator knows exactly which prior steps need to be compensated and in what order. This makes robust error handling much more manageable. Better for complex sagas. For sagas with many steps, complex conditional logic, or branching paths, e.g., if customer is premium, offer express shipping. Otherwise, standard shipping. An orchestrator provides the necessary control and clarity to manage the flow effectively. Disadvantages. Potential coupling. The orchestrator knows a lot about the participating services and their APIs, commands, events. This creates a degree of coupling. If a new service or step is added, or an existing service's interface changes, the orchestrator might need to be updated. This can be mitigated by keeping the orchestrator focused purely on coordinating and not on business logic specific to the participants. Introduces a single point of failure, if not properly designed. The orchestrator itself becomes a critical component. It must be highly available and resilient, requiring robust design for its own persistence, scaling, and fault tolerance. Overhead. Building and maintaining a dedicated orchestrator service, including its own persistence layer for saga state, adds overhead compared to the decentralized nature of choreography. 5.3. Choosing the right pattern. The choice between choreography and orchestration is a significant architectural decision that depends on several factors. Complexity of the saga. Choreography. Best for simple sagas, e.g., 2 to 3 steps, no branching logic, straightforward compensation. Adding more steps quickly makes it hard to manage. Orchestration. Essential for complex sagas with many steps, conditional logic, human approvals, or intricate compensation paths. Number of participating services, choreography, works okay with a few services. Orchestration. Becomes practically necessary when many services are involved, making it difficult to trace events in a choreographic setup. Monitoring and debugging needs. Choreography, generally poor visibility and harder to debug. Orchestration. Highly visible, easier to monitor and debug due to centralized state. Team structure and communication. Choreography can align well with highly autonomous teams that want minimal dependencies. However, cross-team communication for debugging a failing saga can be a nightmare. Orchestration requires one team or a central architectural group to own and evolve the orchestrator, potentially leading to more deliberate cross-team communication, but clearer responsibilities. Existing infrastructure and tooling. Do you have a robust message broker that excels at broadcast events for choreography? Are you comfortable building and managing stateful orchestrator services, or perhaps leveraging specialized workflow engines, which are often orchestration tools? General guidelines. Lean towards choreography when the saga is very simple, involves only a handful of services, and you prioritize maximum decoupling above all else. This can be a good starting point for straightforward reactive flows. Prefer orchestration for most significant business processes in a microservices environment. Its advantages in terms of visibility, control, and explicit error handling typically outweigh the added overhead and the slight increase in coupling. For anything beyond trivial flows, the complexity of managing choreography quickly becomes an anti-pattern. It's also worth noting that hybrid approaches are possible. For example, a high-level orchestrator might delegate a segment of its workflow to a smaller, choreographically managed subsaga. The key is to understand the trade-offs and select the pattern that best aligns with your system's specific requirements and your team's capabilities. With this understanding, we can now delve into the practicalities of building robust sagas, especially focusing on that critical aspect. Compensation logic. 6 building sagas, practical considerations and compensation logic. Moving from theoretical understanding to practical implementation of sagas requires careful attention to detail. This chapter delves into the concrete aspects of designing saga participants, building robust compensation logic, ensuring idempotency, and handling the inevitable failures that arise in distributed systems. 6.1. Designing saga participants. Whether you're building a choreographed or orchestrated saga, the individual services, the saga participants, must be designed to effectively play their role. Atomic local transactions. This is the bedrock of any saga. Each service performing a step in the saga must ensure that its part is an atomic local transaction. This means that within the boundaries of that single service and its own database, the operation either entirely succeeds or entirely fails, leaving its local data in a consistent state. For example, if a payment service is tasked with charging a customer's credit card and updating its internal payment record, these two operations must be a single, indivisible ACID transaction within the payment service's database. If the credit card charge fails, the internal record should not be updated. This ensures that the building blocks of your distributed saga are internally reliable. Handling commands and events. For orchestration, participant services act as command handlers. They primarily receive specific commands directly from the orchestrator, e.g., deduct inventory command, process payment command. After processing the command and performing their local transaction, they publish an event, e.g., inventory deducted event, payment processed event, or a corresponding failure event like inventory deduction failed event. These events are specific replies to the orchestrator to signal completion or failure, allowing the orchestrator to drive the next step. For choreography, participant services act as event listeners. They subscribe to relevant events published by other services, e.g., order created event, inventory deducted event. Upon receiving an event, they perform their local transaction and then publish a new event, e.g., payment processed event, that subsequent services in the chain will react to. Communicating progress and errors. The events published by Saga participants are not just simple signals, they carry crucial information. Event schemas should be thoughtfully designed to convey success or failure, clearly indicate the outcome of the local transaction. Relevant data include any data needed by subsequent steps or for effective compensation. For example, a payment processed event might include the transaction ID, amount, and payment method used. A payment failed event should ideally include a reason for failure, e.g., insufficient funds, card expired. Correlation IDs include a unique Saga ID or correlation ID, often the original order ID or business process ID, in all events and commands. This allows for easy tracing of a single Saga instance across multiple services and message queues, which is invaluable for debugging and monitoring. 6.2 Crafting effective compensation logic. Compensation is where the rubber meets the road for sagas. It's the mechanism that gracefully reverses actions, preventing your distributed system from getting stuck in an inconsistent state when things go wrong. Designing it robustly is paramount. The nature of compensation transactions. Idempotent. Just like forward actions, compensation actions must be idempotent. If the add stock back compensation message is received multiple times by the inventory service, it should only add the stock once for that specific original order. Reversible or provide clear undo. Ideally, a compensation transaction fully undoes the business effect of the corresponding forward action. If a reserve hotel room action was taken, its compensation is cancel hotel room reservation. Defining compensation for each step. For every single forward action in your saga, you must define its corresponding compensation action. This isn't an afterthought. It should be designed concurrently with the forward logic. This often means implementing a pair of API endpoints or event handlers in your service, one for the forward action and one for its compensation. Example compensation cases: forward, deduct inventory, removes items from stock. Compensation, add inventory, adds items back to stock. Forward, process payment, charges customer's card. Compensation, refund payment, initiates a refund. Forward, create shipment, generates a shipping label and notification. Compensation, cancel shipment, cancels the label, alerts shipping provider. Forward, send confirmation email, sends email. Compensation, often no-op or send cancellation email. Some actions are not truly reversible but can be mitigated. Rollback strategy. When a saga fails, the orchestrator, or the reacting services in choreography, must ensure that compensation transactions are executed for all successfully completed preceding steps. The typical strategy is to execute them in reverse order of the forward actions. This helps ensure that dependencies are respected, e.g., you can't refund a payment if the payment wasn't processed in the first place. Consider a saga. Order, inventory, deduct, payment, ship. If ship fails, compensation flow, compensate payment, refund. Compensate inventory, deduct, add stock back. Compensate order, cancel order, mark as failed. The challenge of uncompensatable actions. Not all actions can be perfectly undone, especially those that interact with the physical world or external third-party systems. For instance, once an email is sent, you can't magically revoke it from the recipient's inbox. Or, if a physical product has already left the warehouse, stopping its delivery might be impossible or incur significant costs. Human intervention. For actions that are truly uncompensatable or risky to automate their rollback, the best approach is to design for human intervention. The saga flags itself for manual review, triggers an alert, and perhaps pauses until an operator manually addresses the issue. Designing boundaries. A common architectural pattern is to push uncompensatable or hard-to-compensate actions to the very end of the saga sequence. This minimizes the chance of needing to compensate them. If the saga reaches that final, critical step, it's highly likely that all preceding, more easily compensatable steps have succeeded. 6.3. Ensuring idempotency in saga steps. Idempotency is paramount in distributed systems because message delivery guarantees are often, at least once. This means a message consumer might receive the same message multiple times. Without idempotency, this could lead to disastrous effects, double charges, incorrect inventory levels, etc. Why it's critical? Message duplication. Message brokers might redeliver messages if an acknowledgement is lost or during node failures. Retries. Client services or internal retry mechanisms might resend commands if they don't receive an immediate response. Consumer restarts. A consumer service might process a message, crash, and then reprocess the message upon restart. Strategies for idempotency. Transaction IDS/correlation IDS, the most common approach. Every command or event related to a saga instance should carry a unique identifier, e.g., the order ID or a dedicated saga ID. When a service receives a command event, it first checks its internal state or a dedicated idempotent store, a small database table or cache, to see if it has already processed that specific ID. If so, it simply acknowledges success without re-executing the action. Conditional updates. Design your database updates to be conditional. Instead of update quantity equals quantity X, use update quantity equals quantity X, where id equals Y and quantity equals X. Or insert if not EXISTS. Compare and swap operations. For concurrent updates, use atomic operations that read a value, perform a calculation, and write the updated value only if the original value hasn't changed. Deduplication layer. A separate component that filters out duplicate messages before they reach the main processing logic. 6.4. Handling saga failures and retries. Failures are an inherent part of distributed systems. A robust saga implementation plans for and gracefully handles them. Transient versus permanent failures. Transient failures. Temporary issues like network glitches, database timeouts, brief service unavailability, or temporary resource exhaustion. These often resolve themselves if retried after a short delay. Permanent failures indicate a fundamental problem like invalid input data, logical errors, unauthorized access, or a service being permanently unavailable. Retrying these typically won't help and can even exacerbate the problem. Automatic retries. For transient failures, implementing automatic retries for commands and event processing is crucial. Configurable backoff strategies. Don't retry immediately. Use exponential backoff, waiting an increasing amount of time between retries to avoid overwhelming an already struggling service. Adding a small amount of jitter, randomness, helps prevent all retries from hitting at the exact same time. Circuit breaker pattern. To prevent cascading failures when a service or dependency is consistently failing, implement a circuit breaker. If a service experiences a threshold of failures within a certain period, the circuit opens, meaning subsequent calls to that service immediately fail without even attempting to send the request. After a configured open duration, it moves to a half-open state, allowing a few test requests to see if the service has recovered. If they succeed, the circuit closes. Otherwise, it returns to the open state. Dead letter queues, DLQs, for messages that cannot be processed after a configured number of retries, indicating a permanent failure or an unresolvable transient issue, send them to a dead letter queue. This prevents poison pill messages from blocking the main queue, allows operations teams to inspect why messages failed, debug, and potentially reprocess them manually. Monitoring and alerting for stalled sagas. Implement comprehensive monitoring to track the progress and status of saga instances. Set up alerts for sagas that remain in a pending or in progress state for too long, indicating a stalled process. Excessive compensation events. Messages ending up in dead letter queues. High rates of failed local transactions. Timeouts. Each step in a saga and the saga as a whole should have well-defined timeouts. If a response isn't received within a certain period, the orchestrator service should assume a failure and initiate appropriate error handling or compensation. 6.5 Tools and frameworks for saga implementation. Conceptual. While sagas are a pattern, not a specific technology, certain types of tools significantly simplify their implementation. Message brokers, queues PubSub, essential for asynchronous communication. Tools like Apache Kafka, RabbitMQ, ActiveMQ, Azure Service Bus, or AWS SQS SNS provide the backbone for event-driven sagas, ensuring reliable message delivery and durable storage. State machine libraries. For orchestration-based sagas, modeling the orchestrator's logic as a state machine is highly recommended. Many programming languages offer libraries that allow you to define states, events that cause transitions, and actions to be performed during transitions or within states. This makes the orchestrator's behavior explicit, predictable, and easier to reason about, test, and debug. They are particularly good at handling the various states a saga can be in and ensuring that only valid transitions occur. Workflow engines and business process management, BPM systems. For very complex, long-running sagas, especially those involving human interaction or complex business rules, dedicated workflow engines, e.g., Camunda, Apache Zeeb, Temporal, Activity, or cloud-native solutions, e.g., AWS Step Functions, Azure Logic Apps, can be invaluable. These platforms are designed specifically for orchestrating complex, durable processes. They provide features like visual workflow modeling. Durable execution, state is persisted, so workflow can resume after failures or restarts. Built-in retry mechanisms, timeouts, and error handling. Support for long-running human tasks. Monitoring dashboards that show the progress of running instances. While they add another layer of technology, they abstract away much of the boilerplate required to build a robust orchestrator from scratch. Transactional outbox pattern or atomicity guarantee. When a service performs a local transaction and then publishes an event, these two operations, database update and message publish, must be atomic. The transactional outbox pattern ensures this by storing outgoing events in the service's database as part of the same transaction as the business logic update. A separate outbox relay process then reads these events and publishes them to the message broker. This guarantees that either both the local change and the event publication happen, or neither does, preventing inconsistencies, e.g., order created but event not published, or event published but order not created. By meticulously addressing these practical considerations, developers can build sagas that are not only effective in achieving distributed consistency, but also resilient, observable, and maintainable in the face of real-world system complexities. 7. Beyond sagas, introducing the process manager pattern. In the previous chapters, we've established the critical need for sagas to manage distributed consistency across independent services. We explored the two primary ways to coordinate sagas, choreography and orchestration. If you recall, orchestration-based sagas rely on a dedicated component to manage the flow. This coordinating component is often referred to as a process manager. While the terms saga orchestrator and process manager are frequently used interchangeably, it's beneficial to differentiate them slightly to clarify their scope and purpose. A saga orchestrator is a specific type of process manager whose primary concern is managing the transactional consistency of a distributed business process, especially dealing with compensation for failures. A process manager, more broadly, coordinates complex business workflows, which may or may not have a strong transactional compensational requirement. However, in the context of distributed systems, many complex workflows inherently require transactional behavior, making the overlap significant. 7.1 What is a process manager? A process manager is a conceptual component that coordinates a long-running, multi-step business process across multiple services. It acts as the brain or conductor for a complex workflow. Its primary responsibilities include holding the workflow state. It maintains the current state of a business process instance. For example, for an order fulfillment process, it might track if it's pending, inventory confirmed, payment processed, shipped, or failed. Executing business logic for the process. Based on the current state and incoming events, it decides what the next action should be. This is where the core business flow logic resides. Sending commands to participating services. To move the workflow forward, the process manager sends commands to various independent services, instructing them to perform their specific tasks, e.g., debit account, ship product, reacting to events from participating services. After a service executes a command, it publishes an event indicating the result. The process manager listens for these events to update its state and determine the next step in the workflow. Handling timeouts and failures. It implements logic to deal with services that don't respond or tasks that fail, often triggering alternative paths or compensation logic. Unlike a traditional service that performs a single, well-defined function, like a payment service, a process manager's role is to orchestrate functions across multiple services to achieve a larger business goal. It doesn't perform the actual business logic of deducting inventory or processing payment itself. It delegates these tasks to the relevant specialized services. Analogy: think of an event planner. The event planner, process manager, doesn't bake the cake, cater the food, or play the music themselves. Instead, they coordinate with the baker, the caterer, and the band, the individual services. They know the overall plan, the workflow, track progress, the state, and direct each vendor's next action, send commands. If the baker calls to say they can't deliver, the event planner initiates the contingency plan, failure handling compensation. 7.2 Process Manager versus Saga Orchestrator. A nuance. As mentioned, the terms are often used interchangeably, especially within the context of distributed transactions. However, a subtle distinction can be useful. A saga orchestrator is a specialized process manager focused on ensuring the transactional integrity of a distributed business process. Its primary concern is that either the entire saga completes successfully or it's fully compensated. Error handling and compensation are central to its design. A process manager, in a broader sense, can coordinate any long-running business process, even if it doesn't involve strict transactional semantics or doesn't require complex compensation for every step. For example, a process to onboard a new employee might involve creating accounts in HR, IT, and payroll systems. While errors should be handled, the full compensation of every step might not be as critical as in a financial transaction. In practical terms, for most scenarios where you're dealing with mutable state across multiple services and require consistency, as is often the case with sagas, your process manager will effectively act as a saga orchestrator. The principles discussed for saga orchestration in Chapter 5 directly apply to the implementation of a process manager. 7.3 Why not put process logic in services? One might ask, why do we need a separate process manager? Can't each service handle its part and just call the next service? Yes, that's what happens in choreography. But just as we saw with choreographed sagas, this leads to significant issues for complex workflows. Logic spread thinly. The overall business logic for the process becomes scattered across multiple services. No single service has a complete view of the workflow. Difficulty in monitoring and debugging. Understanding the state of a particular process instance or debugging failures requires tracing messages across many independent components. Fragile dependencies. Changes in one part of the workflow might require changes in multiple services, leading to more brittle designs. A service might accidentally introduce a circular dependency or prevent a logical flow. Reusability issues. If a particular workflow is needed in multiple contexts, duplicating the logic across services or requiring multiple services to perform complex orchestration themselves is inefficient. A process manager brings the coordination logic into a single, cohesive unit, providing a clear focal point for managing the workflow. 7.4 Key characteristics of a well-designed process manager. Workflow state persistence. The process manager must be stateful. It needs to remember where a particular instance of the workflow is at any given moment. This state needs to be persisted durably, so that if the process manager service crashes and restarts, it can resume the workflow from its last known state. Reactive and proactive. It's reactive in the sense that it listens for events from other services. It's proactive in that based on those events and its current state, it issues new commands to other services. Delegation, not execution. A process manager does not perform the actual business operations, e.g., deducting inventory. It delegates these tasks to the specialized services. This adheres to the principle of separation of concerns. Stateless services for operations. Conversely, the services that the process manager coordinates, payment service, inventory service, etc., should largely remain stateless with regard to the overall business process. Their responsibility is to perform their specific local transaction and report the outcome without needing to know the larger flow. Time-aware. Many business processes have time-dependent aspects. A process manager often needs to implement time-based triggers, such as timeouts, e.g., if no payment confirmation within 5 minutes, cancel the order, or scheduled tasks, e.g., send a reminder email after 3 days. Fault-tolerant. Since it's a critical component, the process manager itself must be designed for fault tolerance, handling its own failures gracefully and ensuring that workflows can recover. 7.5 Process manager location and implementation. A process manager is typically implemented as its own service, distinct from the other business services it coordinates. This allows it to scale independently and have its own release cycle. How is it implemented? Often as a state machine. The concept of a state machine aligns perfectly with the idea of a process manager, where a process instance moves through a defined sequence of states based on events and triggers actions. We will explore the details of building process managers using state machines and workflow automation in the next chapter. The process manager pattern provides a powerful and explicit way to manage the intricate dance of a distributed business process. It centralizes the coordination logic, offering clarity, control, and a robust mechanism for ensuring eventual consistency, even when failures occur. It is the logical evolution of saga orchestration, providing a broader framework for managing complex, long-running workflows that are central to many modern applications. 8. Building process managers, state machines, and workflow automation. In the previous chapter, we established the role of a process manager as the orchestrator of complex, long-running business workflows, often embodying the coordination logic of a saga. Now, we dive into the practical aspects of how to build these process managers, with a strong emphasis on state machines as their core design pattern and the broader concept of workflow automation. 8.1 Process managers as state machines. The concept of a state machine is incredibly well suited for modeling and implementing process managers. A state machine, in its simplest form, consists of states, a discrete set of fixed positions or conditions an entity can be in, e.g., order placed, payment pending, shipped. Events, inputs or occurrences that can trigger a change in state, e.g., payment processed, delivery failed, timeout. Transitions, rules that define how an entity moves from one state to another in response to a specific event, e.g., from payment pending to payment processed upon receipt of a payment processed event. Actions. Operations performed during a state transition or upon entering exiting a state, e.g., send deduct stock command, initiate refund. Consider our order fulfillment process as a state machine. Initial state. Order initiated. Event, order placed event. Action, send deduct stock command to inventory service. Transition to state, inventory deduction pending. Current state, inventory deduction pending. Event, stock deducted event. Action, send process payment command to payment service. Transition to state, payment pending. Current state, inventory deduction pending. Event, stock deduction failed event. Action, send cancel order command to order service. Notify customer. Transition to state, order failed a terminal state. Current state, payment pending. Event, payment processed event. Action, send create shipment command to shipping service. Transition to state, shipment pending. Current state, payment pending. Event, payment failed event. Action, send return stock command to inventory service, compensation. Send cancel order command to order service. Notify customer. Transition to state. Order failed a terminal state. This approach offers significant benefits: clarity and understandability. The flow of the business process is explicitly defined. Anyone can look at the state machine definition and understand how the process moves through its life cycle. Predictable behavior. Valid states and transitions are strictly enforced, reducing the likelihood of unexpected behavior or invalid states. Easier maintenance. Changes to the workflow logic involve modifying the state machine definition rather than scattered conditional logic across multiple services. Robustness. State machines inherently handle unexpected events by simply ignoring them if no valid transition is defined from the current state for that event. They also make it easier to add error states and compensation paths. 8.2. Building a process manager step by step. Implementing a process manager typically involves these components. Process definition. This is the blueprint of your workflow, defining the states, events, transitions, and actions. It can be code-based, using if-else statements, switch cases, or dedicated state machine libraries in your chosen programming language, e.g., stateless for C, xstate for JavaScript, various libraries for Java Python. This is often the quickest way to start for simpler workflows. Configuration-based DSL, defining the workflow using a domain-specific language, DSL, in a configuration file, e.g., YAML, JSON. This often works well with generic workflow engines. Visual editors. Many advanced workflow engines offer graphical interfaces to drag and drop elements and define the workflow visually, which then generates the underlying code or configuration. State persistence. A process manager is inherently stateful. For a long-running process, its current state must be stored durably, so that if the process manager service crashes or restarts, it can pick up exactly where it left off. This usually means persisting the current state, along with any relevant context data, e.g., order ID, customer ID, amount, to a database. Command sender. This component is responsible for dispatching commands to the various services that participate in the workflow. This typically involves sending messages to a message broker, a queue or topic that the target service is listening to. Event listener. This component subscribes to events from the participating services. When an event is received, it triggers the process manager to advance its state according to its defined logic. Example, flow with persistence. Incoming request event. The process manager receives an initial request to start a new workflow, e.g., customer places an order. Load state. It checks if a workflow instance for this order ID already exists. If not, it creates a new instance with an initial state. If it exists, it loads the last known state from its database. Apply event transition. The process manager's state machine logic is applied. Based on the current state and the incoming event, e.g., order placed event, it determines the next state and any actions to perform. Execute actions. It sends commands to relevant services, e.g., deduct stock command. These commands, and their unique correlation IDs, are often queued within the process manager's internal outbox before being sent externally to ensure atomicity with state updates. Save state. the process manager updates its internal state, e.g., from order initiated to inventory deduction pending, and persists this state, along with any relevant context, to its database. This is critical for durability and recovery. Loop. The process manager then waits for the next relevant event from a participating service to trigger the next transition. 8.3 Workflow automation with dedicated engines. While you can roll your own process manager using a state machine library and a database for persistence, this approach requires significant effort to handle all the intricacies of a durable, fault-tolerant workflow. This is where dedicated workflow engines or business process management (BPM) systems come into play. These platforms are built specifically to manage complex, long-running processes. They offer features that abstract away much of the boilerplate, allowing developers to focus on defining the business logic of the workflow. Key features of workflow engines: durable execution. Workflows are inherently durable. Their state is persisted at every step, meaning they can survive process restarts, server reboots, and network outages. The engine ensures that a workflow instance continues exactly where it left off. Visual modeling. Many engines provide graphical tools, often based on BPMN business process model and notation, to design workflows, making them intuitive for both technical and business stakeholders. Built-in resilience. They offer out-of-the-box features like automatic retries with exponential backoff, time-based triggers, timers for timeouts, delays, and robust error handling. Scalability. Designed to manage millions of concurrent workflow instances. Monitoring and analytics. Provide dashboards to observe the progress of active workflows, identify bottlenecks, and track key performance indicators. External task orchestration. They don't typically run the business logic directly. Instead, they coordinate external workers, your microservices, by sending commands and waiting for results. Human task management. Some engines support explicit human tasks, allowing workflows to pause and wait for manual approval or data entry before proceeding. Examples of workflow engines: conceptual descriptions. Apache ZB/Camunda platform. These are open-source workflow engines that focus on orchestration native microservices. They are highly scalable and robust, designed to integrate seamlessly with event-driven architectures. They allow you to define processes using BPMN diagrams, which are then executed by the engine, triggering your services via commands and reacting to events. Temporal/cadence. These are fault-tolerant workflow platforms that allow you to write your workflow logic directly in code, e.g., Go, Java, TypeScript, Python, using SDKs. They provide a durable execution environment, meaning your code can literally pick up where it left off after any system crash or network partition. This feels more like writing regular code, but with the guarantees of a powerful workflow engine behind it. Cloud-native services, e.g., AWS Step Functions, Azure Logic Apps. Managed services provided by cloud vendors that allow for defining serverless workflows. They are highly scalable and integrate well with other cloud services, abstracting away much of the infrastructure. When to use a dedicated workflow engine: very rich, complex workflows. Many steps, conditional logic, parallel branches, human tasks. Long-running processes spanning days or weeks, where durability is paramount. High demand for visibility and audit trails, to see exactly where each instance is and what paths it took. Compliance and regulatory requirements, for processes that need strict enforcement and auditability. When rolling your own, state machine infrastructure becomes too burdensome. 8.4 Implementing logic within the process manager. Regardless of whether you use a simple state machine library or a full-fledged workflow engine, the core logic within your process manager, or saga orchestrator, will typically involve decision logic. Based on the current state and the incoming event, decide the next action. This involves conditional statements, checks for valid transitions, and potentially evaluating business rules. Command issuance. Sending specific commands to the appropriate downstream services. These commands should contain all the data necessary for the service to perform its local transaction. Compensation triggering. If a failure event is received, The process manager must consult its definition of compensation logic to issue the correct compensation commands to previously completed steps. Saga completion failure notification. Once the saga reaches a terminal state, either fully completed or fully compensated failed, the process manager should publish a final event, e.g., order processed successfully, order processing failed, to notify other interested parties. Building process managers as state machines, whether through custom code or dedicated workflow engines, provides a robust and explicit way to manage the inherent complexity of distributed business processes. They are the backbone of orchestration-based sagas, providing the necessary control and visibility to handle the nuances of eventual consistency and fault tolerance. In the next chapter, we will delve deeper into critical aspects like error handling and idempotency, which are fundamental to the reliability of these complex workflows. 9. Error handling, idempotency, and reliability in distributed workflows. Building sagas and process managers to orchestrate complex distributed workflows is a powerful approach. However, their true value is realized only when they can operate reliably in the face of the myriad ways things can go wrong in a distributed system. This chapter focuses on critical aspects often overlooked in simpler designs: robust error handling, the absolute necessity of idempotency, and other patterns for building resilient distributed workflows. 9.1. The inevitability of failure in distributed systems. In monolithic applications, or single machine systems, developers often assume that a function call will either return a value or throw an exception. The network, however, shatters this assumption. When service A makes a call to service B, several outcomes are possible. Success: service B processes the request and sends a successful response. Failure: service B processes the request and sends an error response. No response, due to network partition or service B crash. Service A's request may or may not have reached service B. If it did, service B may or may not have processed it. Service B may or may not have subsequently crashed. Slow response: service A eventually gets a response, but it takes an unacceptably long time. This uncertainty, especially in scenario 3, is why naive retry mechanisms and lack of idempotency can lead to disastrous consequences. 9.2. Robust error handling strategies. Effective error handling in sagas and process managers involves a multi-pronged approach. 9.2.1. Retries with backoff and jitter. This is the first line of defense for transient failures, temporary network glitches, brief service unavailability, momentary database contention. Fixed retries. Simple but potentially harmful if the issue persists. Exponential backoff. Instead of retrying immediately, wait an increasing amount of time between retry attempts, e.g., 1s, then 2s, then 4s, 8s, etc. This gives the struggling service time to recover and prevents overwhelming it with a flood of retries. Jitter. Add a small, random delay to the exponential backoff time. This prevents all retrying instances from hitting the recovering service at exactly the same moment, creating another thundering herd problem. Where to apply retries. When a process manager sends a command to a participating service. When a service itself calls a dependency during its local transaction. When consuming messages from a queue, the message broker typically handles retries and dead lettering for unacknowledged messages. Important considerations. Retry limits. Define a maximum number of retries beyond which a failure is considered permanent and requires different handling. Timeouts. Ensure each operation has a reasonable timeout. Beyond this, the request is considered failed from the caller's perspective. 9.2.2. Circuit breaker pattern. The circuit breaker pattern adds resilience by preventing repeated attempts to call a failing service, which could worsen the problem, a cascading failure. It helps give a service time to recover. Closed state. Requests are allowed to pass through to the service normally. Open state. If the failure rate or number of consecutive failures exceeds a threshold, the circuit opens. All subsequent requests fail immediately without even attempting to call the service. This protects the failing service from being overwhelmed and fails fast for the calling component. Half-open state. After a configurable time period, e.g., 30 seconds in the open state, the the circuit transitions to half open. A small number of test requests are allowed to pass through to the service. If these requests succeed, the circuit closes, signaling that the service has recovered. If they fail, it immediately returns to the open state. Implementing circuit breakers directly in every service that communicates with another can be complex. Often, these are provided by client-side libraries, API gateways, or messaging middleware. 9.2.3 Dead Letter Queues, DLQs. For messages or commands that cannot be processed after exhausting all retries, indicating a likely permanent failure or a persistent problem, they should be moved to a dead letter queue, DLQ. Purpose: prevent blocking. Keeps poison pill messages from clogging the main processing queue and holding up other valid messages. Investigation: provides a dedicated location for operations teams or developers to inspect failed messages, understand why they failed, and manually intervene, e.g., fix data, requeue after a bug fix. Audit trail acts as a record of permanently failed processing attempts. 9.3 The absolute necessity of idempotency. We touched upon idempotency in Chapter 4, but its importance cannot be overstated. An idempotent operation is one that can be applied multiple times without causing different effects beyond the first application. Why is this non-negotiable in distributed systems, particularly when dealing with retries and eventual consistency? Message duplication. Message brokers might deliver the same message more than once. This happens due to network issues, consumer crashes, or broker restarts, where the message was processed by the consumer but the acknowledgement was lost. System retries. If a service or a process manager retries sending a command because it didn't receive a response, that command might have actually succeeded the first time. Client retries. The client application might retry an operation, unaware that the first attempt partially succeeded. Consequences of non-idempotent operations: double payments charges, sending a process payment command twice. Incorrect inventory levels, deducting stock multiple times for a single order. Duplicate resource creation, creating the same user account or order multiple times. Broken business logic, inconsistent state that is hard to recover from. How to achieve idempotency, revisited for emphasis. Unique request IDS/correlation IDS. Every command, event, or request related to a specific business operation, like an order or a money transfer, should carry a unique identifier. When a service receives such an operation, its first action is to check if it has already processed this specific ID. It can store these processed IDs in a dedicated idempotency store, a database table, a RIDI's cache, etc. If the ID is found and the previous operation was successful, the service simply acknowledges success without re-executing the logic. If the ID is found, but the previous operation was unsuccessful or still in progress, specific recovery logic might be triggered. Conditional updates/predicate checks. Many database operations can be made idempotent by adding conditions. For example, instead of update balance equals balance 100, use update balance equals balance 100 where transaction init processed equals XYZ. Or for state transitions, update order status equals shipped where order it equals ABC and order status equals packed. Use idempotent verbs. In design, prefer operations that are naturally idempotent. PUT, create or update a resource at a given URI, is often inherently more idempotent than post, create a new resource, in res tful APIs. Critical point: idempotency must be designed and implemented at the service level, within each participating service that performs part of the saga. The process manager cannot magically make a non-idempotent operation safe. The individual service receiving the command must handle the idempotency internally. 9.4 Ensuring reliability and observability. Beyond error handling and idempotency, several other practices contribute to a reliable distributed workflow. 9.4.1 Transactional outbox pattern. When a service performs a local database transaction and then needs to publish an event based on that transaction, these two operations must be atomic. If the database update succeeds but the event publication fails, or vice versa, you end up with an inconsistent state. The transactional outbox pattern solves this. Instead of directly publishing the event to a message broker, the service stores the outgoing event in its own database as part of the same ACID transaction as the business logic update. A separate, dedicated outbox relay process, often a lightweight background worker, periodically queries this outbox table. It then publishes the events from the outbox to the message broker. Once successfully published, the events are marked as so or removed from the outbox. This guarantees exactly once event publication, from the perspective of the application, by leveraging the atomicity of the local database transaction. Either both local change outbox entries succeed, or neither does. 9.4.2 Observability, monitoring, logging, and tracing. You can't fix what you can't see. In complex distributed workflows, robust observability is paramount. Centralized logging. All services should log relevant events, command receipts, and outcomes to a centralized logging system. Crucially, logs should include the Saga ID or correlation ID so that you can easily trace a single Saga's journey across all services and time. Distributed tracing. Tools like OpenTelemetry, Jaeger, or Zipkin help visualize the flow of requests across multiple services. They generate unique trace IDs that are passed along with each request, allowing you to see which service called which, how long each step took, and where errors occurred. This is invaluable for debugging slow or failing sagas. Business process monitoring, BPM, saga state tracking. For process managers, dashboards that show the current state of all active saga instances, their progress, and any stalled or failed instances are essential. This provides real-time operational visibility into your core business processes. Metrics like average saga duration, number of completed sagas, and number of compensated sagas are vital. Alerting. Set up proactive alerts for sagas that become stuck in an intermediate state for too long, e.g., no state change or event for X minutes. Messages accumulating in dead letter queues. Excessive compensation, attempts for a particular saga type. High error rates in specific saga steps. 9.4.3 Data reconciliation and manual intervention. Despite all the automated resilience, there will be edge cases, unexpected data issues, or truly uncompensatable actions. For these, design clear processes for manual intervention and data reconciliation. Have clear runbooks for operations teams when sagas fail in specific ways. Provide tools or UIs that allow operators to inspect the state of a failed saga, manually trigger compensation steps, or mark a saga as completed with manual intervention. Consider eventual reconciliation processes, e.g., daily batch jobs, that cross-check data consistency across services for critical invariants that cannot be strictly guarded by real-time sagas. Building distributed workflows that are truly reliable is a journey of continuous improvement. By embracing the inevitability of failure and implementing these robust strategies for error handling, idempotency, and observability, you can build systems that not only recover from problems gracefully, but also provide the transparency needed to understand and continuously enhance their resilience. 10. Monitoring, testing, and deploying complex workflows. Building sagas and process managers is only part of the challenge. For these complex distributed workflows to be successful in production, they must be rigorously monitored, thoroughly tested, and deployed with strategies that minimize risk and ensure continuous operation. This chapter covers these crucial operational aspects. 10.1 Monitoring complex workflows beyond the basics. Traditional service monitoring, CPU, memory, latency, error rates, is a good start, but for sagas and process managers, you need to monitor the business process itself. This means understanding the state and progress of each workflow instance. 10.1.1 Key metrics and KPIs. Saga completion rate. Percentage of sagas that complete successfully versus those that lead to compensation or failure. A drop in this rate indicates a systemic issue. Saga duration/latency. The time it takes for a saga to complete from start to finish. Long-running sagas may have different expected durations than short ones, but unexpected spikes indicate bottlenecks. Saga step duration. Time taken for individual steps in a saga. pinpoint slow services or external dependencies. Number of sagas in each state. For a process manager, this shows the current workload and where processes are getting stuck, e.g., too many in payment pending, too few reaching completed. Compensation rate. Frequency of compensation events being triggered. A high rate suggests underlying problems in the forward path, misconfigured processes, or unreliable dependencies. Retries and dead letter queue, DLQ, volume. High numbers here indicate persistent issues with message processing or service stability, requiring investigation. Service-specific business metrics. Each service participating in a saga should expose metrics relevant to its specific domain, e.g., inventory reduction success rate, payment gateway response time, shipment tracking errors. 10.1.2 Tools and techniques. Distributed tracing, recap. Essential for understanding the flow of a single saga instance across multiple services. Tools like OpenTelemetry, Jaeger, or Zipkin allow you to stitch together logs and metrics based on correlation IDs or trace IDs. This helps visualize dependencies and latency in individual steps. Centralized logging. Aggregate logs from all participating services and the process manager into a single platform, e.g., Elk Stack, Splunk, Datadog. Ensure logs include correlation IDs for easy filtering and searching by saga instance. Business process monitoring, BPM, dashboards. For orchestration-based sagas and process managers, build custom dashboards that visualize the state transitions of your workflows. Funnel charts. Show conversion rates between stages of a saga. Heat maps. Highlight which saga instances are stuck or taking too long. Instance-specific views. Allow drilling down into a particular saga instance to see its full history, current state, and associated errors. Alerting systems. Configure alerts on deviation from normal behavior for all the KPIs mentioned above. Alerts should be actionable, leading to clear remediation steps or investigation procedures. 10.2 Testing complex workflows, a multi-layered approach. Testing sagas and process managers requires a shift from traditional unit and integration testing focused on a single service. You need robust testing strategies that span multiple service boundaries and simulate real-world failure scenarios. 10.2.1 Unit tests, individual code components. Process manager orchestrator logic. Test the state machine logic in isolation. Verify that given a specific current state and incoming event, the process manager correctly transitions to the next state and prepares the correct commands. Saga participant logic. Test that each service correctly processes its commands, performs its local transaction, and publishes the correct events. Also, test their compensation logic in isolation. Idempotency logic. Unit test the idempotency checks within each service to ensure that duplicate messages are handled correctly without side effects. 10.2.2 Component integration tests, service to service. Service API contracts. Ensure services adhere to their command and event contracts, schema validation. Message exchange. Test that services correctly send and receive messages from the message broker. Point-to-point interactions. Test that Service A can successfully send a command to Service B, and Service B responds with the expected event. These tests can use mocked dependencies for other services. 10.2.3 End-to-end (ETWI) workflow tests, full saga execution. These are the most critical tests for complex workflows. They simulate the entire saga execution across all services, including the process manager and message broker. Happy path scenarios. Verify that the full saga completes successfully from start to finish. Failure and compensation scenarios. Crucially, test all possible failure points and ensure the saga correctly compensates. Simulate a failure in a specific service, e.g., by making it return an error or making its message broker connection fail. Verify that the compensation logic is triggered and executes correctly, bringing the system to a consistent state. Test intermittent failures that require retries. Test uncompensatable actions and human fallback paths. Boundary conditions. Test with minimum-maximum values, edge cases in data, etc. Tools can involve spinning up all relevant microservices in a dedicated test environment, often using containerization, e.g., Docker Compose, Kubernetes in Minikube. Test frameworks automate interactions, assertions, and cleanup. 10.2.4 Chaos engineering and resilience testing. Beyond planned tests, introduce controlled failures into your production, or very close to production, environment to proactively identify weaknesses. Kill random services. See how the sagas react when a critical participant randomly disappears. Inject network latency failures. Mimic realistic network conditions. Overload services. Test how sagas handle throttling or slow responses. Tools. Chaos engineering platforms, e.g., Chaos Monkey, Litmus Chaos, help automate these experiments. 10.3 Deploying complex workflows. Strategies for success. Deploying systems with sagas and process managers requires careful consideration to maintain availability and safely introduce changes. 10.3.1 Independent deployment of services. A core tenet of microservices is independent deployability. This applies to your Saga participants and the process manager itself. Each service should be deployable without requiring a coordinated deployment of all other services. Backward compatibility of contracts. Ensure that changes to events and commands between services are always backward compatible. This allows older versions of consumers to work with newer versions of producers and vice versa, for choreography, and new versions of an orchestrator to work with older versions of services. Schema evolution. Utilize tools and practices for evolving your message schemas, e.g., Avro, Protobuf, or simple JSON with careful versioning, to ensure that adding fields or making non-breaking changes doesn't disrupt running systems. 10.3.2 Rolling updates and blue-green deployments. Rolling updates. Gradually replace old instances of a service with new ones. This minimizes downtime by ensuring some instances of the old version are always running while the new version comes online. Blue-green deployments. Spin up a completely new environment, green, with the new version of your services, keeping the old environment, blue, running. Once tests on green are successful, switch traffic to green. If issues arise, traffic can be instantly switched back to blue. This requires more resources but provides near-zero downtime and quick rollback. 10.3.3 Database migrations and schema evolution for process manager state. The process manager's internal state, in its database, is critical. Migrating its schema requires careful planning. Non-blocking migrations. Avoid long-running schema migrations that lock tables in production. Use techniques like adding nullable columns first, then populating, then making them non-nullable. Backward-forward compatibility. Ensure that old versions of your process manager code can still read the new database schema during a rolling update, and that new versions can read the old schema. Data migration for state changes. If a Saga's definition changes, e.g., a new step is added mid-flow, you might need to write data migration scripts to update existing Saga instances in the database to reflect the new state machine definition. This is one of the more complex aspects of evolving long-running workflows. 10.3.4 Graceful shutdowns and startups. Shutdown. Services should gracefully shut down, completing in-flight requests and stopping new ones from coming in. For services acting as event consumers, this means signaling to the message broker that they are stopping consumption and releasing their leases. Startup. Services should start quickly, connect to dependencies, message broker, database, and begin processing requests. For process managers, this means being able to pick up pending workflows from their last known state. 10.3.5 Canary releases. A gradual rollout strategy where a new version of a service is deployed to a small subset of users or traffic first. If successful, it's rolled out to more. This minimizes the blast radius of potential issues. Monitoring is the feedback loop for successful deployment. Without it, you're deploying blind. Robust testing ensures confidence, and intelligent deployment strategies minimize risk. Together, these practices are foundational for managing the operational complexities introduced by sagas and process managers in a production environment. 11. Real-world applications. Case studies in sagas and process managers. Theory is one thing, but seeing how sagas and process managers are applied in real-world scenarios brings their power and necessity to life. This chapter explores several common business domains and illustrates how these patterns are used to build reliable and resilient distributed systems. 11.1 Case Study. E-commerce order fulfillment. This is perhaps the quintessential example for sagas and process managers due to its multi-step nature and critical financial implications. The business process. A customer places an order on an e-commerce website. The system needs to create an order record, deduct quantity from inventory, process the payment, generate a shipping label and dispatch, send a confirmation email to the customer. The challenge? Each of these steps is handled by a separate microservice, e.g., order service, inventory service, payment service, shipping service, notification service, each with its own database. A global ACID transaction is impossible. If any step fails, prior successful steps must be compensated to avoid inconsistencies, e.g., paid for an item that's out of stock or deducted stock for an unpaid order. Saga implementation, orchestration-based process manager. An order saga manager, process manager service, is responsible for coordinating the entire workflow. Initial step, customer places order. The front end calls the order service, which creates a pending order and publishes order created event. The order saga manager subscribes to order created event. Upon receiving it, it creates a new saga instance, persists its state as order initiated, and sends a command, deduct stock command, to the inventory service. Inventory deduction. Inventory service receives deduct stock command. It performs its local transaction, deducts stock, and publishes stock deducted event or stock deduction failed event. Order saga manager receives the event. Happy path. If stock deducted event is received, it updates saga state to inventory confirmed and sends process payment command to the payment service. Failure path. If stock deduction failed event is received, e.g., insufficient stock, the order saga manager updates saga state to order failed. It then sends a cancel order command to the order service, compensation, and triggers send order canceled notification to the notification service. Payment processing. Payment service receives process payment command. It performs its local transaction, charges card, and publishes payment processed event or payment failed event. Order saga manager receives the event. Happy path. If payment processed event is received, it updates saga state to payment confirmed and sends create shipment command to the shipping service. It also sends send order confirmation command to the notification service. Failure path. If payment failed event is received, the order saga manager updates saga state to order failed. It triggers compensation, sends add stock command to inventory service to add back stock, sends cancel order command to order service, triggers send order failed notification to notification service. Shipping and completion. Shipping service receives create shipment command. It performs its local transaction, generates label dispatches, and publishes shipment created event or shipment creation failed event. Order saga manager receives the event. Happy path. Shipment created event completes the saga. The order saga manager updates saga state to order completed. Failure path. Shipment creation failed event triggers compensation, add stock, refund payment, cancel order record, and notifies the customer. Benefits. Financial integrity. Prevents scenarios where a customer pays but doesn't get the product or gets a product without paying. Data consistency. Ensures inventory and order statuses are always aligned across services. Resilience. The process can recover from failures at any step without corrupting the overall state. Visibility. The order saga manager provides a single point to track the status of any order. 11.2 Case Study. Financial transactions, bank transfers. While simplified in earlier chapters, bank transfers are a classic use case for sagas, particularly when moving money between different accounts, potentially in different banks or different internal ledgers. The business process. Transfer money from account A to account B. The challenge. Account A and account B are typically managed by separate services, e.g., account service A, account service B, or even separate financial institutions. An atomic two-phase commit is typically not available or desirable due to the high volume and required low latency. Saga implementation, choreography, or orchestration. Choreography example. Account service A debits account A and publishes account debited event account service B, receives account debited event, credits account B, and publishes account credited event. If account service B fails to credit and publishes account credit failed event, account service A, or a dedicated compensation service, receives account credit failed event and compensates by crediting account A back. Note: for critical financial systems, choreography becomes quite risky due to visibility and debugging challenges. While simpler, it's rarely chosen for core banking. Orchestration example, more common and recommended. A transfer saga manager, process manager, coordinates the flow. Initial step, request to transfer money received by transfer saga manager. It sends debit command to account service A. Account service A responds with account debited event or debit failed event. Transfer saga manager logic. If account debited event, send credit command to account service B if debit failed event. Saga fails, no compensation needed as nothing was committed. If account credited event from account service B, saga completes successfully. If account credit failed event from account service B, send credit back command, compensation, to account service A saga fails. Benefits: high availability. Transfers can proceed even if one account service is temporarily slow, relying on eventual consistency. Distributed ledger harmony ensures both accounts reflect the transaction correctly or are restored to their original state. Auditability. A well-designed orchestrator provides a clear trail of events and state changes for each transfer. 11.3 Case study: travel booking system. Booking a trip is a multi-service operation involving flights, hotels, car rentals, and potentially activities, often from different providers. The business process: book a complete travel package. The challenge: each booking, flight, hotel, car, is a local transaction with its own unique failure modes and compensation needs. Customers expect an all-or-nothing outcome from their perspective. Saga implementation, orchestration-based. A travel booking saga manager orchestrates the process. Steps: book flight, send book flight command to flight service. Book hotel. If flight successful, send book hotel command to hotel service. Book car. If hotel successful, send book car command to car service. Confirm booking. If all successful, send confirm travel command to consolidate. Compensation logic examples. If book car command fails, travel booking saga manager sends cancel hotel command to hotel service and cancel flight command to flight service. Compensation. If book hotel command fails, travel booking saga manager sends cancel flight command to flight service. Compensation. Uncompensatable consideration. Some bookings might have cancellation fees. The compensation logic would need to reflect this, e.g., refund partial amount or flag for manual review for fee management. The saga would ensure that the customer isn't left with a partially paid for a broken trip. Benefits: atomic experience for user. The user perceives the entire booking as a single transaction despite its distributed nature. Resource management ensures that resources aren't held unnecessarily if the full package can't be booked. Flexibility: easily add new booking types, e.g., tour, cruises, by integrating new services into the orchestration. 11.4 Case study: healthcare patient onboarding. Patient onboarding workflows often involve multiple departments, systems, and potential human verification steps, making them inherently long-running and asynchronous. The business process: onboard a new patient involving creating patient record, verifying insurance, scheduling initial appointment, setting up portal access, assigning primary care physician, PCP. The challenge: different systems manage patient data, insurance, scheduling, and provider assignment. Human tasks introduce significant delays. Failures might mean a patient is partially onboarded, leading to frustrated experiences. Saga implementation: process manager with human tasks and timers. A patient onboarding process manager is ideal here, often implemented with a robust workflow engine that supports human tasks and timers. Steps: create patient record, automated step with patient service. Verify insurance, human task, assign task to insurance verification queue. Process manager waits for insurance verified event or insurance rejected event. This might include a timer timeout 24H to escalate if not completed. Schedule appointment. If insurance verified, send schedule appointment command to scheduling service. Set up portal access. Simultaneously, send create portal account command to portal service. Assign PCP. Send assign PCP command to PCP service. Compensation alternative paths. If insurance verification fails, the process doesn't compensate prior steps, e.g., patient record creation usually isn't undone. Instead, it forks to an enrollment failed path, notifying the patient and internal staff for manual follow-up or alternative options. If appointment scheduling fails, perhaps the process manager tries to schedule with a different provider or flags it for human intervention. Benefits. Visibility into complex flow. Provides a clear overview of where each patient is in the onboarding journey, important for large healthcare providers. Robustness to human delays. Workflows don't break waiting for human tasks. They simply persist their state and resume when the human input arrives. Automation of repetitive tasks. Automate standard data creation and initial setup, freeing up staff. Handling forks and joins. Can manage parallel processes, e.g., portal access and PCP assignment can happen concurrently. These case studies underscore that sagas and process managers are not abstract academic concepts. They are pragmatic, indispensable patterns that directly address fundamental challenges in building reliable, consistent, and scalable distributed systems for some of the most critical applications in business and beyond. They provide the architectural blueprint for managing the inherent complexity of modern software landscapes. 12. Future trends and best practices for distributed system design. As we reach the conclusion of our exploration of sagas and process managers, it's clear these patterns are fundamental to building robust distributed systems. However, the landscape of software engineering is constantly evolving. This final chapter will summarize key best practices and look ahead at emerging trends, ensuring you're well-equipped to navigate the future of distributed system design. 12.1 Key Best Practices for Sagas and Process Managers. Let's consolidate the most important takeaways from our journey. Embrace eventual consistency. Recognize that strong, immediate acid consistency across independent services is usually infeasible and often undesirable. Design your systems with base principles in mind and explicitly manage the eventual consistency states. Prioritize compensation from the outset. Compensation logic is not an afterthought, it's central to saga design. For every forward action, define its compensation. Consider the uncompensatable actions and plan for human intervention or strategic placement of those steps at the end of the saga. Insist on idempotency. Assume messages will be duplicated and operations will be retried. Design every service operation to be idempotent. Use unique request IDs and implement checks to avoid unintended side effects. Choose orchestration over choreography for complexity. While choreography offers higher decoupling, its lack of visibility and debugging challenges make it best suited for very simple, linear sagas. For anything beyond trivial flows, orchestration with a dedicated process manager provides superior control, visibility, and simplifies error handling and evolution. Model process managers as state machines. State machines provide a clear, explicit, and robust way to define the lifecycle of a business process. This approach enhances predictability, maintainability, and makes debugging much more straightforward. Leverage message brokers reliably. Message brokers are the backbone for inter-service communication in sagas. Ensure their reliability, consider message durability, and implement the transactional outbox pattern to guarantee atomic updates and event publication. Invest heavily in observability. Instrumental in understanding the behavior of complex distributed workflows. Implement centralized logging with correlation IDs, distributed tracing, and specialized business process monitoring dashboards. Alert on anomalies and stalled processes. Design for failure with resilience patterns. Assume services will fail, networks will be unreliable, and messages will be lost or delayed. Implement retries with exponential backoff, circuit breakers, and dead letter queues. Test at all levels. Beyond unit and integration tests, Focus on end-to-end workflow tests that simulate both happy paths and, critically, failure and compensation scenarios. Consider controlled chaos experiments to uncover vulnerabilities. 10. Evolve with backward compatibility. As your systems grow, sagas and their underlying services will evolve. Strict adherence to backward-compatible API contracts, commands and events, and thoughtful schema evolution are essential for independent deployability and graceful updates. 12.2. Future Trends in Distributed System Design. The evolution of distributed systems is relentless. Here are some key trends influencing how we'll build and manage complex workflows in the coming years. Continued rise of workflow engines and orchestration platforms. As microservice architectures mature, the need for robust, managed workflow solutions will only grow. Dedicated workflow engines, like Temporal, Cadence, Apache Zeb, Camunda, are becoming increasingly sophisticated, offering durable execution, advanced error handling, and visual modeling out of the box. Cloud-native workflow services, AWS Step Functions, Azure Logic Apps, also continue to expand their capabilities. Expect more powerful, opinionated platforms that abstract away the lower-level complexities of distributed choreography. Emphasis on developer experience, DX. Building resilient distributed systems has a steep learning curve. The future will likely see more tools and frameworks that simplify the development of sagas and process managers, providing higher-level abstractions and reducing boilerplate code. This includes SDKs for workflow engines that feel more like writing regular application code rather than managing complex messaging protocols. Event streaming and event sourcing expansion. Event streaming platforms like Apache Kafka are becoming central nervous systems for many distributed architectures. Event sourcing, where the state of an application is stored as a sequence of immutable events, is gaining traction. This deepens the reliance on events, making patterns like sagas, which are inherently event-driven, even more natural to implement. Process managers could be built directly by reacting to and emitting events from an event stream. Artificial intelligence, AI for operations, AIOps. Managing vast, complex distributed systems will increasingly rely on AI to analyze logs, metrics, and traces. AIOps will help detect subtle anomalies, predict failures, and even suggest, or trigger, automated remediation for issues within sagas and workflows, moving beyond simple threshold-based alerting. Focus on data consistency and reconciliation. While eventual consistency is fundamental, there will be continued innovation in tools and techniques for ensuring data integrity across distributed data stores, especially for analytical purposes. This might involve more sophisticated data reconciliation pipelines and smarter caching strategies. Edge computing and serverless workflows. As computing extends to the edge and serverless architectures become more prevalent, the need for orchestrating workflows that span cloud, edge, and on-premise environments will grow. Workflow patterns will adapt to manage interactions across these diverse deployment models. Standardization and interoperability. Efforts like the Cloud Event Specification aim to standardize event formats, which will further improve interoperability between services and make it easier to build and integrate sagas across heterogeneous environments. Conclusion: orchestrating the future. The journey through sagas and process managers reveals a fundamental truth about modern software. Complexity is inherent in distributed systems, but it can be managed and even embraced. We no longer build single-system strongholds. We build networks of resilient, collaborating services. Sagas and process managers are not just patterns, they are a mindset. They force us to confront the realities of distributed computing. The network is unreliable. Services can fail, and data consistency is a challenge. And to design our solutions with these realities in mind. They transform the daunting task of guaranteeing business integrity across a web of independent components into a manageable and reliable process. As you embark on your own distributed system design endeavors, remember the lessons learned. Prioritize compensation, demand idempotency, test rigorously, and observe continuously. By mastering these principles and staying attuned to emerging trends, you will be well equipped to orchestrate the increasingly complex and fascinating world of distributed systems and build the resilient, scalable, and reliable applications that power the future.